Hi, and welcome to 3.5b Horizontal Projectile Motion 2. In this lesson, students will be able to calculate and fully describe the motion of a horizontally fired projectile. So now we could jump right into one of these word problems because we know what the concepts are from the previous lesson. So it says a hungry coyote is fired horizontally from a cannon at the top of a 100-meter tall cliff with an initial speed of 50 meters per second. How much time does it take the coyote to hit the ground? What is the coyote's range? And with what velocity will the coyote hit the ground? Look at that crazy coyote. Do you guys even know who that is? That's Wile E. Coyote. So for these projectile motion problems, I always like to start by drawing a diagram. So here's our cliff, and it says that it's a 100-meter tall cliff. So this is 100 meters. We could even call that D. Should we use a subscript at this point? dy for the y direction, right? And then you could just draw the coyote as a circle, doesn't matter. And we'll draw the initial speed by making a velocity vector. Now it says it's launched, or the coyote's launched horizontally. So that means our velocity vector should be horizontal, pointing just to the right. And the velocity is equal to 50 meters per second. Now, would you say that velocity is pointing in the x or the y direction? It's horizontal, so I would say it's pointing in the x direction. So I use my subscript whenever possible. So that's the situation, and here's the ground, and we're going to draw the path of the projectile, which is a parabola. Okay, so right now we know the vertical displacement is actually, I'll draw it like this. All right, negative 100 meters because you're going downward, and we know the velocity. So now we have a nice table. We could even plug in, if we wanted on the table, a is equal to negative 9.8 meters per second squared, kind of like we did in the free fall, but remember that the acceleration is in the y direction because of gravity. Gravity's pulling you downward. This is vertical. All right, the next step is to write down the given information. And if you remember from the free fall videos, I wrote all the information again. Now I'm going to write the information again in an x, y, t chart. So I call it a t chart here. Okay, and the x and y chart is going to be the same every time for these projectile motion problems. Let's start with the y. We started the year talking about displacement. Then we talked about velocity. And then we talked about how if your velocity changes, that means you're accelerating. We also have time. Now I write time down here because the time is the same in the x and y direction. All right, it's the same thing. That's the only thing that's always the same. Okay. In the x side of things, and I'm actually going to move the acceleration there. So the x direction, this is dx. We don't know what the range is yet, but we can calculate it, okay? How far does it go from the base of the cliff? What's the range? What's the displacement in the x direction, okay? And from yesterday, so now I'm going to do the same thing. I'll write the velocity. Yesterday we talked about how this velocity doesn't change. The horizontal velocity stays the same. So we don't have to write VI and VF because it's the same. It's going to be 50 meters per second the whole time. And if it's 50 meters per second, we kind of know the average velocity too. 50 plus 50 divided by 2. The average is 50 meters per second. And this is going to be helpful because on the X side of things, we're always going to be able to use the average velocity is equal to d over t. This equation here. That's what we're going to use. So the last step is to write in our subscripts just to make sure we keep everything safe. These are the X side of things, and this is all on the Y side of things. Then I like to go boom, 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 and now we're ready to plug in what we know. So a good place to start is always going to be the acceleration in the y direction is negative 9.8 meters per second squared, unless you're on some other kind of planet, if it specifies it. Then you look at what's told in the problem. It's a 100-meter tall cliff, and we said that's going to be the y direction, the y displacement, 100 meters. Now, what direction is the coyote going? Is the coyote going up or down? The coyote's going down, so we better make sure that we make the displacement negative. All right. What is another number that they give you? They tell you that the velocity, the speed, is 50 meters per second. So are we gonna, we have three choices here in our diagram, in our table. Are we gonna write the 50, where are we gonna write it? It's pointing horizontally. It says it's launched horizontally, so we're gonna put it in the horizontal direction, 50 meters per second there, okay? That is all the numbers that they tell you, and then the obvious one is the acceleration, okay? But there's another piece of hidden information there. Just like when we did the drop problems, the free fall problems, tell me about the velocity in the y direction in the very beginning. All of the velocity is pointing in the x direction, but this velocity vector isn't pointing up or down at all. There's no y component of the velocity. And if there's no y component, that means that the initial velocity is 0 meters per second in the y direction. But in the x direction, it is moving across at 50. It's just not moving downward yet. It has to accelerate. So that's the main setup. And if you set yourself up correctly, then the rest of it is pretty much just kinematic equations. Because you have to compartmentalize. You look at this side separately, then you look at this side, and you just try to fill in the blanks using the kinematic equations. So that's the technique that I like to do. So let's start. It says part A, how much time? So we're looking for the time. Would it be more beneficial to look at the x side of things? Well, on the x side of things, I only have one variable that I know, so that's not going to be too useful. Or should we concentrate on the y side of things? Look how much information we know on the y side of things. We have 3 pieces, so that's going to be enough. Right now, we don't care about VF. So let's find that equation without VF in it, and that's D is equal to VIT plus 1/2 AT squared. And remember, this is on the y side of things, so you could even write your subscripts so that you don't accidentally plug in the x. No, you don't want to do that. This is VIY. So this is negative 100 is equal to VIY is 0. So that's going to cancel with the time. Luckily, otherwise you'd have to do the quadratic equation, which is fair game for this class. And you're looking for t squared. So this goes away. You do a little algebra. And you get 4.5, really 4.517, 4.5 seconds, we'll round it, okay? So this is powerful information. The time is very powerful information because as soon as you plug in the time over here, not only are you getting more information on the y side of things, but the time is the thing that links the x and the y together. So now we have 2 pieces of information on the x side of things, and we can calculate dx, which is part B. It says, what is the range? And remember, the range is how far are you going downfield? What is the range? Okay. And I mentioned before, since we know the velocity is constant, that means we know the average velocity. And if we know the average velocity, we can use this formula. The average velocity is equal to the displacement over the time. That's the first formula that we learned this year. It's on the top of page 6 in your reference table. So this is 50 is equal to, oh, I should call this x, and this is x, but I don't put a subscript on the time because it's the same, 4.5 seconds. So dx, the range, is equal to 225.9 meters. Okay, so we could plug that in our table, and now we're starting to know a lot of good stuff about our situation here. Okay, then it says, with what velocity will the coyote hit the ground? Okay, so you could probably tell from our table, we're going to be looking for VFY. That is true, but that isn't the full story. That's not the full story. If you zoom in on what's actually happening here, let's zoom in over here. Okay, here's the ground. The coyote is moving horizontally still with a velocity of 50 meters per second. But now the coyote is going to have some vertical velocity, VFY, because he's picking up speed because it's accelerating downward. So you have a final velocity that's pointing downward. We could calculate what that is, but that's not the actual final velocity. The actual final velocity is the resultant of these two vectors. So this is like a kind of a multi-step problem here. First, you find what is the y component, and then you could find the final velocity. This is the final velocity here, this resultant vector. So that's the game plan. I'm going to erase this other stuff. And now we can start the first of the two-step problem for part C. So we are looking for VFY, that's over here, and we have 4 pieces of information. So we kind of have a choice as to which formula we want to use. Since the time is rounded, I'm going to use these 3 pieces of information. So if we want an equation without time in it, we're going to have to use VF squared is equal to VI squared plus 2AD. So this is the y side of things, and we're looking for VFY is equal to, this is just 0, so that's convenient, that's going to go away, plus 2 times negative 9.8 times negative 100. And you get VFY, remember to take the square root, and you get 44.3 when you round it, meters per second. And remember that final velocity is pointing downward. So when you take the square root, you just make that negative. So we can now plug that in. Our XY table is fully filled in, but we still didn't answer the question. The question says, what is the resultant velocity? Well, it actually just says, what is the velocity? And you have to know, they're looking for the resultant of the y component, 44.3 meters per second, and the x component. So these two velocity vectors added together give you your actual final velocity. So this is a right triangle, and we're just going to use Pythagorean's theorem. Or I should say the Pythagorean theorem, and you substitute in. And you get a resultant velocity of 66.78. We'll call it 66.8 meters per second. So when you add those two together, you get 66.8 meters per second. But remember, velocity is a vector which has a magnitude and a direction. So let's find this angle here by using the inverse tangent. We'll substitute in, and you get 41.5 degrees. So that's equal to 41.5 degrees right there. And our final velocity, you could say it's 66.8 meters per second, 41.5 degrees, and we'll call that here. See how this is the horizontal, and we're going below the horizontal. It's that many degrees below the horizontal. So you could either write out below the horizontal, or you could just write BTH, and I'll know what you're talking about. BTH stands for below the horizontal. I wouldn't call this north, south, east, or west anymore because, this could be pointing in the northern direction right now. Think about the situation. Maybe he's being fired north or south or east or west. We don't really know. It doesn't specify, but we do know that this is the horizontal. So that's kind of how we'll name these velocity vectors. Along with this, what would this angle be if you wanted to say above the horizontal, possibly? It would actually be the same thing because it's alternate interior angles. So if you wanted to say above the horizontal, it's exactly the same way to name the angle, and that's fine. I say below the horizontal a lot of the time because if you look at the vector, it's like starting there and going this way. And just like we have in the past, I choose the angle that's near the beginning of the vector. So I like to say below the horizontal. For this next problem, I want you to please pause this video. I know I've been talking for a long time, 15 minutes. They say, Mr. Nangle, keep the video short. But you know, the point of this part of the video is for you to pause it so you're not watching the video anymore and do the problem on your own. And then I'll show you how to do it and you can see if you got it right. Okay, so pause the video and then we'll do the problem. So the Royal Gorge Bridge in Colorado rises 321 meters above the Arkansas River. Suppose you kick a rock horizontally off the bridge. The magnitude of the rock's horizontal displacement is 45 meters. So that's dx. They're giving you different physical quantities now. But just like on the previous one, they also gave you dy. And they say find the speed at which the rock was kicked. That's this initial velocity. Tricky stuff. So I like to make the diagram. I'll plug in what I know. I'll even write in this velocity vector. This is what we're looking for, Vx. What is the horizontal velocity? And now I'll look at my XY table. I highly recommend taking the, 10 seconds to set up this table each time you do a problem. I think it's a great way to organize your thoughts. So dy is negative 321 meters. This is 45 meters. They're looking for this. We don't know the time. So as soon as I see this, I'm like, okay, I'm looking for something on the x side of things. I really want to do v is equal to d over t, but I don't have the time. So the first thing I have to ask myself is, can I figure out the time? So what else do I know on the y side of things? Well, I know the acceleration is negative 9.8 meters per second squared. And just like before, the initial velocity in the y direction is 0 meters per second. Don't forget about that. That's probably the most hidden of the information in these types of problems. I explained why VI was 0 in the previous problem. So now that we have 3 pieces of information here, I could find the time using our equation that does not have VF in it, and writing in our subscript so we don't get confused when we plug in our displacement. It's the 321 displacement. So negative 321 equals this big mess. And then when you solve, you do some algebra. Don't forget to take the square root and you get about 8.1, a little less than 8.1 seconds. That's a long time for a rock to be falling off the cliff. That was a super tall bridge. Did you see that on the last slide? 8 seconds. Count to 8 for really quick for yourself. Yeah, that's a long time. That's a very high bridge. Okay, so this, like I said in the previous problem, this is very powerful information because now we can use it to analyze the x side of things, which is really what they're looking for, the horizontal velocity. And on the x side of things, we're always going to use v is equal to d over t because we're not accelerating. There might be problems in the future where it tells you you're accelerating in the x direction. But unless it tells you, you can use this equation every time. And I know that's good news to some people because it's like, oh, Mr. Nangle, can I use this every single time? More often than not, I'm going to say, no, you got to look at the situation. But unless they tell you that that you're accelerating in the x direction, I'll let you use this because you're not accelerating, so you can use this equation. And you'll get a horizontal velocity of only 5.6 meters per second. So you're just kicking the rock off the side of the bridge. Okay, so hopefully you got that on your own. If you didn't, hopefully that explanation made sense. That's about it. Thanks for watching and have a great day.